I'd like to start off this event with a quote. Learn continually. There's always one more thing to learn. This quote was said by Steve Jobs. A very good afternoon to everyone gathered here. We all are here today to learn something new that's going to stay with us forever and have a great impact on us. I, IIChE AD, welcome our chief guest of the day, Dr. Hanno Brümmer, Dean Dr. K.S. Rajan, School of Chemical and Biotechnology, respected professors, alumni members, students, external participants, and volunteers gathered here. The Department of Chemical Engineering at Sastra was established in the year 1994. The first edition of CAPE happened in the year 2013, before which the IIChE Students Chapter of Sastra conducted a symposium called Prakriya in the years 2011 and 2012. With the enormous response received from the student members, Prakriya paved the way for CAPE from the year 2013. The objective of this conference is to provide an interdisciplinary forum for researchers and engineers to share and discuss their ideas on emerging issues in process engineering. The conference paves the way for the student community to interact with eminent industrialists and academicians from all over the globe. This time, it's planned to conduct guest lectures from esteemed speakers of various fields, paper presentation, and technical events, which will help the students in exploring various fields. Further, DWSM workshop aims at giving basic insights to design a process flowsheet and simulate it with ease. Once again, I formally welcome the speaker of the day, Dr. Hanno Brümmer, Senior Vice President, Polyurethanes Global Head of Production and Technology at Covestro, Leverkusen, Germany. Now moving ahead, I request Mr. Dharani Shebi to introduce our chief guest for the day. Please take over.
Good afternoon, everyone. It is my great pleasure to be amongst the first to welcome you to this CAPE event. It is indeed a beautiful afternoon, all soaked in the delighted frame of mind. This afternoon, I have the delight of introducing the guest of honor and the speaker of today's occasion, Dr. Hanno Brümmer. Dr. Hanno Brümmer is a Senior Vice President heading Production and Technology at Covestro. With his enthusiasm for educational strengthening, Dr. Brümmer finished his diploma in chemistry from Westphalisch Wilhelms University, Münster, in 1992. He further went on to receive his PhD in chemistry in 1995. Holding the title as a PhD chemist, Dr. Brümmer started his career at Bayer in 1996. At the beginning of his research career, Dr. Brümmer then worked in various production facilities at various locations in Germany and in Baytown, Texas, USA. Dr. Brümmer has been the Senior Vice President, Global Head of Production and Technology for Covestro's Polyurethane Division since 2015. This includes isocyanates, polyether polyols, as well as basic chemicals like chlorine. Dr. Hanno Brümmer is a member of the Management Board of World Chlorine Council, Eurochlor, and of the European Institute of Industrial Leadership. I also welcome our Dean, School of Chemical and Biotechnology, Dr. Rajan sir, all of the faculty members, alumni, external participants, the last but not the least, my friends and fellow students. I welcome you all.
Thank you, Dharanish. As a token of gratitude, I'd like our Dean to give consent to present the memento to our chief guest. Memento will be displayed on the screen and the same, will be sent to you, sir.
Thank you.
Now I kindly request Dr. Hanno Brümmer, Senior Vice President, Polyurethanes Global Head of Production and Technology at Covestro, Leverkusen, Germany, to deliver his guest lecture on Process Innovation in Industrial Chlorine Production. Please, sir. And I kindly request the participants to raise their questions in the chat box, if any. Please, sir.
Yeah, thank you very much. Thank you very much for the invitation again. It's great to see such a large group here this afternoon. I very welcome you all. It's my honor to be invited to this conference on process engineering. So I gladly accepted when I was contacted. It's always interesting for me to interact with students around the world. Thank you very much. Let me share my screen so that you can see the presentation. Hold on. Sorry about that. I don't think that's it. Hold on once again. Can you see my screen yet?
It is sharing.
Okay, maybe it takes a second.
Yeah.
But you see.
It's just a black screen. There's nothing.
Okay. Let me try again. Let me know when you see a presentation.
Yeah, I think now it's coming. Yes, perfect.
It's coming?
Yeah, it's
Okay.
coming.
Very good. Very good. Sorry about the delay. Very good. Okay. Thank you very much. Again, very warm welcome. Glad I can speak today about process innovation in chlorine production. And why did I choose this example? Because for me, it tells a nice storyline about a very old, very well-known process. It has been around for many, many years, but still we were able in recent years to make a big step in efficiency development. As introduced, I'm heading globally at the company Covestro, the production and technology area for polyurethanes, which is the largest business within Covestro. To get a little idea, this encompasses around 15 sites and locations around the world. But as I cannot speak about this today in whole detail, if you are more interested in what it means, where I am, which topics I care about, I would also refer you, maybe check my Instagram, because there will be always frequent updates. As a public listed company, I just have to advise you, and sorry, this is a legal statement I have to do. Of course, this today is about an innovation story about Covestro. It's not meant to be read as forward-looking statements in order to prevent any kind of hint how good the company will be doing in the future. So what will I speak about today? First, I will introduce you a little bit about the role of chlorine in the industry and why is it important and what kind of impact chlorine has as a chemical. Then I will speak about this new technology, the so-called ODC technology that we have developed over more than 20 years, and also not speak only about the chemistry, but especially about the industrialization development. And there you will learn that it takes much more to develop the chemistry, but a lot of process, material, other topics have to be tackled in order to bring a process, let's say, from the lab, from the pilot to full industrial scale. And then in the end, I will show you it took a long time. On the other hand, it allowed us to develop a platform about technology which can be used beyond chlorine for many, many more, also very modern and attractive applications. Or to put it in a simple questions, you cannot increase efficiency by 25% on an established process. We said, why not? And hopefully I convince you today it is possible. So let me talk about chlorine and what it means for the industry. Chlorine is a very versatile chemical in the industry. On the other hand, as an end consumer and an end customer, you will never buy chlorine, and that's for good reason. It's a highly reactive, also highly toxic and aggressive chemical. So why is it such a large chemical if nobody needs it? Well, it's actually intermediate. It's a highly energized molecule, which again then allows a lot of reactions to take place. And that's why chlorine has been around in the chemical industry, although you don't find it in its pure form in finished products. And in order to show where chlorine all plays a role, we like to show the so-called chlorine tree. The chlorine tree shows you how from one base chemical, which is the salt, so the normal rock salt, the salt is the same as you have in your food or you find in the ocean, from this one basic chemical, through producing chlorine, an array of substances and materials are being produced. And you see basically the entire area what chemistry covers, from dyes which have been around as long as chemistry around, to materials, fibers, but even modern pharmaceuticals and agrochemicals. You also see here, and that's depicted by the color code, let's say about half of these products contain chlorine, as you would expect, because we're using chlorine in the synthesis. On the other hand, the other half does not even contain chlorine. Again, maybe the question comes up, why is chlorine so important if it's not in the finished product? Again, chlorine is a highly energetic molecule, so it's used on its way in order to make certain materials, for instance, although in the end it does not end up in the final product, but is brought back. And I will show you examples for that. And as I mentioned, chlorine has been around for a long time. So I give you a brief history on chlorine and chlorine chemistry. You see it's been far more than 100 years. Interesting wise, the first chlorine production process described was in 1866, the Deacon process, a process which then never made it to industrialization. It had to do with the choice of catalysts that had to be developed. And it only was rediscovered, let's say, in the last 20 years and brought to full scale. The success story of chlorine is very much coupled with electrolysis, meaning taking electric current and producing from salt chlorine. That's the classical process that probably most of you learned also in your chemistry studies. And it started even in the late 1800s with diaphragm electrolysis, later developed to the mercury, which was a good process. On the other hand, we all know the effect of mercury on its toxicity, on its environmental impact. So by now, mercury is fading out. In Europe, it has been completely banned. Also in most other regions of the world, mercury is, for good reason, being replaced. Later on, also HCl electrolysis was developed. And then you see in the 2000s, a lot of developments, again, the ODC technology, which I will describe today, but also the revival of the Deacon catalysis. And now you see that world production in 2018 has reached 80 million tons. From this 80 million tons, almost nothing is sold only as intermediate between companies. Everything else is in the tree, which I showed before. And there has been, of course, on the long time, over the 100 years, been two major drivers for process improvement. One are the environmental and safety and health aspects, as I spoke about, especially around mercury and abandon mercury from these processes. The second one was the energy demand. As I described, chlorine is a highly energetic molecule. Rock salt has a low energy. That means you have to put in a lot of energy. You cannot beat thermodynamics. You have to put in the energy to get this energetic molecule, and that energy you have to be generating. So looking at this picture from the energy part, and maybe it's easier to start from the right, you see the products from the chlorine tree, for instance here, foam materials or stadium roofs out of polycarbonates. Going back, as I mentioned, about 80 million tons of chlorine are being produced for everything in the chlorine tree. And that then takes, as you see, 240 million megawatts, or you could say 240,000 gigawatts or 240 terawatts, a unit which is rather rarely used, but for these kind of energies actually finds application. And that in turn, if that is a fossil energy, as it is mostly today, it will have the equivalent of 120 million tons of CO2. So it's a story of energy demand, and thereby becoming also a story of CO2 and environmental impact. I think with these figures, it becomes very clear why driving energy demand to lower energy demand in chlorine synthesis has been around as long as the industrial process has been around. What does it mean for Covestro? Covestro, our company, is a typical company that actually uses a lot of chlorine, but the finished products don't contain it. Our products are polyurethanes, the business I work for, which make about 50% of the company. So our sales in this area are roughly 6 billion euros on a total company about between 12 and 14 billion. Our second largest sector with 3 to 4 are the polycarbonates, and both of those product groups do not contain chlorine. They use chlorine in the production process. Our smaller coatings, adhesives, and specialties units has some very few products like chlorinated rubber, which actually contain chlorine, but also there, the majority of products, which are isocyanates, do not contain chlorine. On the other hand, as chlorine is needed, also the energy demand of Covestro is mainly determined through the chlorine process. And you see that depicted on the right. About 60% of our total energy demand at Covestro has to do with the synthesis of chlorine. Now taking you to the processes. And you have to understand, and you will see this in the course of my presentation, that there is not only one chlorine process. It has to do with the raw materials you start from, mostly from rock salt, that is then called chlor-alkali synthesis. There's also processes which start from HCl as a full recycle process. The advantage, you don't have byproducts. On the other hand, some of the byproducts which are being produced, like caustic soda, are also highly needed in the industry. So there's not one choice. But what you see here, and from left to right, you also see the development in history. For instance, look at the first line, the chlor-alkali electrolysis. You see that from mercury through membrane, through ODC electrolysis, how the energy demand, the specific energy demand on kilowatt hours per tons of chlorine can be reduced significantly. When you look today, a modern ODC electrolysis cuts the energy demand for the same amount of chlorine in half. On the HCl recycle, you can even achieve a bigger step. You see with a modern decant process, the energy demand actually goes down to 25%. So what's the story behind this ODC? ODC stands for oxygen depolarized cathode. So 3 terms. Oxygen, you know, the chemical ubiquitous in our air. Depolarized cathode is then the material that we use on the electrode in order to get the oxygen to react. And the principle is quite simple. On the left-hand side is the process, as I mentioned before, you should all well know, the classical process. You have a solution, which is called brine, of sodium chloride in water. You apply electricity, and with that solution, just from rock salt in water, you produce chlorine. You also produce caustic soda, and you produce hydrogen. This just comes through the stoichiometry in the anode and cathode room. And the voltage, because this is important, that's why I mentioned it, in order to make this process happen, is about, let's say, 3 volts at a current density of current. The ODC now puts an additional layer in this electrochemistry room, depicted here by the blue room. And in the blue room, we introduce oxygen. That oxygen then, as you see here, is being reduced for the caustic soda, suppressing the hydrogen production. So yes, you get one product less. In the end, you end up with chlorine and caustic soda, but when you look at the benefits, they are significant. It sounds only like 1 volt. You go from 3 to 2 volts, but look at the percentage. You're talking easily about 25% less energy demand for the same process. And this is the basic concept that was developed in our laboratories a long time ago. And now I will tell you about the story, bringing it from this conceptual idea to an industrial production. Before I do that, I want to quickly sketch how all these processes developments in principle happen. Also to get an understanding which kinds of steps it takes, which kind of scale you have to pass, but also what kind of timeline you see with that. So this rather generic chart applies to many process developments, but it gives you a little bit more an idea. Sometimes we get the question, why does it take so long to go from the laboratory to a full scale? Well, if you have your idea, if you have your basic concept working, like we say, you have your conceptual design, meaning what I showed you on the chart before, and it works, you then have to validate it into a significant amount. So you're still in gram or kilogram scale, but you have to really look for what are my process conditions? What is my process window in order to make this happen? You're still in the lab, but you're doing, let's say, multiple lab experience. And these days, there will also be automation. There will be a lot of data analysis in order to really understand the window or the structure relationship from the different process parameters. Once that is successful, you go in usually what we call a mini plant. A mini plant still looks somehow like a laboratory plant. It will be still inside a building, let's say inside a laboratory hood, probably but full scale 2-3 meter laboratory hood, but it already uses real tubing. It already has everything connected, and it already allows to run not an experiment 1 by 1, but a continuous run at least for hours or even days, 24 hours, to see how the process now in continuous flow develops. This is usually a phase where we actually also try to find the difficulties. So you purposely push the reaction to its limits to see what kind of temperature, pressure, flow rates are actually hindering the production or actually have a negative impact in order to, again, verify the window of operation and really to see things early. You don't want to have major process problems later on in the larger plants. The mini plant is the scale where you feel you're already working in process mode, but you can easily rearrange, really easily re-engineer and get all the problems out of the way early. If that is successful and your window has narrowed, then you go already to the so-called demo plant. The demo plant can either be the plant that you want to build in the future, just smaller scale, so small reactors, small distillation column, but everything set up like you would build it in large scale. On electrolysis, that usually means, since you have electrolyzer cells, you build them to full scale, but you don't put as many. You don't put an entire room of electrolyzers, but you only put one in, but then use the periphery of the production in order to really see that in a production environment. That's also the reason why these so-called demo plants are often put in the production unit, maybe in one specific field. Then you can use everything around. You also get all the raw materials on industrial quality to really to see, is it working or which kind of things you still have to work on. And if all of this is happening, then you might decide to build a full-scale plant. And then you're talking again about easily about 5 years, because in order to build a full-scaled, more than 100,000 ton plant, You start with a permit, you need to develop the scope, you go through all the engineering package, and then you're looking at typically maybe 12 to 30 months of construction, depending on the complexity and the startup. So that's why you can imagine this easily. If you only take 2-3 years for each of those steps, plus the final build, it's difficult to do this entire thing, let's say less than 10 to 15 years. So what does it mean in ODC production? And you see here 2 lines, and that is on purpose, because it also shows that we were fastly developing. On the other hand, we hit a roadblock. The invention I spoke about earlier, we made in the lab in the 90s. And you see, 5 years later, we went to something which we called a bench cell, or in the picture I showed before, we would say this was pilot, mini plant, pilot scale. Very successful, worked very nicely. So we built a pilot electrolyzer. Again, in the terminology I used before, you would say a demo plant. This is operating, this has the side of a full electrolyzer, just not so many cells as a full electrolyzer has. But depicted here, we hit a stop. What happened? The reaction worked nicely. The energy demand was as desired. The chlorine quality was as desired, but the performance of, let's say, the machinery of the electrolyzer was not as desired. The cells we were operating did not have the stability and the long time endurance that you need. I give you a flavor what the expectation is. Typical full-scale industrial processes, whether it's chemical or petrochemical industry, but let's say in the chemical industry, typically have to be able to run 5 years. And it doesn't mean Monday through Friday, it means 5 years. They should be running 5 years, maybe some small interruption needed for some minor maintenance, but they should be able, from their stability, from the design, to run 5 years. Then you might have a large, what we call shutdown, turnaround, where everything is opened, inspections, also legal tests are being done, and then it runs another 5 years. That's why not only the chemistry, but all the materials that you use have to be designed in order to be able to run those 5 years. And here we hit the problem because the electrodes we were using were degrading. The performance was deteriorating over time, and we were not able, we saw on the projection, we would not be able to design something with that expectation. So we had to go back to the laboratory. And again, in 2000, we're back to the laboratory. 5 years later, we were successful to pilot, and another 6 years later, we built the second demo electrolyzer. So pretty much from here to there, it took us 11 years to get back where we were, but now we were successful. Now we had an electrolyzer and we had a material developed that was fulfilling our expectation and beyond. And that's why after this demo electrolyzer was running and still being tweaked and optimized for several years, we then decided to build a full-scale production plant, which is currently in construction in Tarragona, in our site in Spain. And this will be the first industrial full-scale, larger than 100,000 ton chlorine plant based on this ODC technology. I look at the scale, we're talking 30 years from the first innovations being done in the laboratory. And what was the key? Giving you a little bit more detail about the key, what it took. The old or first generation electrolyzers were based on carbon. So we had carbon-based ODCs. They were coated with silver, but they did not have the lifetime expected. So it also took more than the chemistry of the chlorine production. Now we had to dig into the chemistry of the material of the electrode selected. And by testing, by optimizing, by choosing and developing with external company the right material, in the end, we were able to develop a new system on a polymeric sheet or mesh with a special find of silver being dotted on that. And that electrode then delivered both on performance, but also on stability. And as it showed here, this took us another 8 years. And also the process had to be developed. These are not kind of electrodes you can buy from manufacturers, again, because they were very specifically designed. So the process, taking silver oxide, because that's the key of the catalyst material, and the polymeric matrix, PTFE, a fluorinated polymer, how this would be in a reactive mixing process, how then that powder would be sprinkled on the support, how the power later was adjusted and pressed in order to end up, and this is one so-called ODC sheet. All of these process steps had to be developed. This was nothing off the shelf, so we are far beyond the chemistry. We're now into developing a manufacturing process, you could say, of an equipment or of a machine. But that's what it takes. Getting only the chemistry right is not enough. So we were also working, as you probably can imagine, with companies and experts on these kind of powder technologies, absorption technologies, pressing technologies, and now we have a fully running, let's say, machine that can produce these ODCs as a standard material with very high, very consistent quality. Still not done. We had the right material, we had the right performance. On the other hand, going on the large demo electrolyzers, we saw another issue. We saw that ideally the reaction was happening, but not all the way around the electrolyzer cell. So what happened here? We analyzed, and this is a picture from what you saw before on the very surface of the cathode, where you have the oxygen part and the liquid part. And we saw ideally, like shown here in the middle, this is what should happen. You should have a phase layer, and on the phase layer, the reaction with the oxygen should happen to produce the materials what we want. Unfortunately, as we saw, and these electrolyzers have 3 to 4 meters high, that on the top we had oxygen breakthrough, and on the bottom we had liquid breakthrough. And we were not able, by just changing the diameters, to simply design it that all of these were working. So in the end, we are missing effectivity, because only the pores in the middle were ideally working as designed, but the pores on the edge, on top of bottom, we were losing. So overall, the overall effectiveness of our electrolyzer was limited. So we solved the chemistry, we solved the materials. Now it was really about process design, or you could say process simulation, even designing of things with pressures and liquid flow. Also here, we developed a solution. By analyzing the situation, as shown on the picture before, we had a gradient around the entire cell where only the middle part was performing and penetration was on the bottom and the top as undesired. The solution was we needed a counter falling film flow. That then prevents the flooding in one or the other direction by either liquid pressure or gas pressure. So we were designing a system where actually sodium chloride, which is the raw material, and the caustic itself as a diluted solution, which is then enriched to the reaction, were counterflowing in several films. It also there, you can imagine, took a lot of process design in order to make this happen. And I give you a little glance how this looks. This is again a picture a little bit larger. And what we had to do was this so-called percolator system was introduced, which is a mesh, as you can see here, with a gold-coated mesh that had to be introduced in order to make this now multi-layer design happening. You see here our partner in this entire storyline, as I told you, was ThyssenKrupp. ThyssenKrupp Uhde, now called ThyssenKrupp Uhde Chlorine Engineers even, has been a very, very reliable partner for us, taking it once from the innovation that was at that time Bayer, the company that Covestro was originating from, taking it to the industrial scale. They have a lot of process development experience, and with our partnership, we were able to make this even more complex, but now very reliable apparatus happen. And now you see here a couple of pictures from ThyssenKrupp, how now from the electrodes, which I showed you before, which the manufacturing process we optimize, now the cell process, where you make from several of these sheets, you make one big sheet of an electrolyzer cell, and then you assemble all of these cells into this big frame here, and that the entire thing that you see here with all the tubing, this is one electrolyzer that you see. And then depending on the scale that you need for your full plant, you will have maybe 2, 4, 6, 8 of these large electrolyzer boxes in one, what we call cell room. And that then will be the erection part of the full chlorine plant. So what does it all mean for the energy demand and our development? I talked about this before. As I said, we had all these processes available. On the other hand, we faded out the mercury process, and you see how nicely with these developments on the energy, we were still able to compensate the growth which we had to the growth of our finished product, and the specific energy demand decreased by building more and more of the newer technologies. And here's the landscape of Coestro's chlorine production. We are a global company, we have global reach. Our headquarters is in Europe, as we are originated from the European Bayer company. And you see there's a couple of plants in Germany that use either the classical membrane or already had then piloted the ODC technology. In Brunsbüttel, for instance, we have HCl process. In Baytown, we have chlor-alkali. And in Caojing, we have HCl and also the Deacon process. In Tarragona, a smaller plant in Europe, this is where we then decided to build a full-scale plant based on this technology. So that our total capacity is going from 2.1 million to 2.7 million tons of chlorine that we are planning to produce, again, as intermediate for our polymer materials. Then with all these processes available, question might raise, will you now replace all the chlorine production in all the plants that you just seen with ODC technology? And the answer is no. And why is that? Please remember, it always depends what you need in a specific location, what is your demand, what's your situation. And I will carry you very quickly, very basically through the consideration that you have to take. It depends what is your current power demand. But when you look at the profitability of a project, it takes a lot more. You will have an investment in order to build the plant. And these bars are just symbolic. Don't take now specific numbers to it. So that will be, let's say, negative on your bank account. Then you have to invest in oxygen. Do you have oxygen? Is it available? Or do you have to build an air separation unit in order to get to the oxygen? So the cost of getting the oxygen for the ODC process has to be in your consideration. Then comes the value of the hydrogen. I told you the key of this technology is to suppress hydrogen. So what's your value of the hydrogen? And there's two basic areas where hydrogen can go. You can use it chemically for so-called hydrogenation reactions. Then it doesn't make sense to suppress the hydrogen, because if you still need it, then you would have to buy extra hydrogen from another source. If you don't need it, then hydrogen can of course be used as an energy source, but it turns out the balance of suppressing the hydrogen and saving the energy in the chlorine production versus then incinerating the hydrogen to generate energy is the better choice. So if it's a pure energy story, usually your mathematics, your financial consideration will turn out that it makes a lot of sense then to build ODC. So all of this on your electricity saving, on the CO2 price, let's say equivalence, you have to take on your positive side. And then if your result is overall positive, then it's the right choice to build ODC. But as I described, there could be factors actually showing no membrane is the right choice, and using the hydrogen, for instance, for aniline production could be a better choice. Or maybe you don't have access to sodium chloride, but you have to build a recycle process like we have in China, where it makes then the most sense to build a decant plant. As I showed you before, the decant plant actually has the lowest energy demand on a recycle process. So again, not one process for all. You have to take everything into account on your investment calculation and shows which has the most value created. What is the right selection for a specific site, for a specific demand? For Tarragona, it turned out to be the right choice to have ODC. We don't have a chemical use for the hydrogen. We have high energy costs, and that's why what all of our experience that went into the demo scale that we had in Uerdingen in the middle of Germany developed up to 20,000 tons. We then put into a full-blown industrial scale production, and this is what we are investing currently. We will have, of course, the energy savings, and to put this into equivalent, we will see an energy CO2 equivalent savings of more than 20,000 tons of CO2 per year, because for our plant there, we are building our 130,000 ton full-scale plant. And if you could take a look right now in Spain into our Tarragona plant, you will see construction is fully ongoing. You see the plant being erected with a central electrolyzer room and all the periphery, and all this is strongly continuing. In the very last part, I want to briefly talk about beyond. I showed you what it all took in order to bring chlorine production from the lab, from the ODC to full scale. On the other hand, we learned so much on the way. We learned so much about materials. We learned so much about the electrode that we really ended up with a platform, a technology platform, where you can even take the chlorine away and think about what else can I use this platform for? Because I understand now this electrode, it's a gas diffusion electrode. There's a gas reaction happening with electricity, and easily there's a lot of concepts developing for them, also for very modern applications. For instance, we are now thinking and working on the so-called power to chemistry. Electricity, as we know, is the key thing that is being produced by renewable energy, whether it's wind energy or solar, you get electricity. Usually you cannot use directly electricity in chemical reactions because most of them need heat or steam. With this technology and with this nice activation with choosing the right electrode, maybe a different catalyst, we are investigating currently how to activate CO2. That would really be a major milestone for the chemical industry, because we could be using something which is a nice carbon raw material, but very hard to activate, very difficult to bring to reaction. But we can show already that CO2 in a gas diffusion electrode can then be used for making classical chemistry. So we can close the carbon cycle. Other applications include disinfections of water, and companies are developing very small scale water disinfectants, which can maybe use with a solar cell and then produce clean water. And we know clean water for all, clean drinking water is one of the major goals, also here depicted number 6 of the United Nations sustainability goals. And further ones go in battery applications, which are of course also a major driving force for sustainable industry and for sustainable living. And a little bit more detail about the power to chemistry. So we're using CO2, we are using renewable energy, and here you see a typical selection of molecules which can already be produced on laboratory scale, but they can be produced with CO2 and electricity. For instance, syngas, which is an important building block for products, formic acid, formaldehyde, methanol, ammonia, all berry-based chemicals. They have their own tree. I showed you the chlorine tree. They all have a tree and go into many final products that we are all using in our daily life. So this platform has really shown us, opened us the door for very much new chemistry, all based on sustainable energy and a free carbon source, saving oil and gas. So summarizing, hopefully I could show you today that chlorine is an essential chemical for the industry. It's not been sold directly, but it is part of the tree and on the network. I could hopefully show you that this ODC technology we developed, we were able to make a significant step in reducing the energy demand of this process. I showed you that it takes the chemistry, but then it takes material science, machine development, process development, assembly technology, all of this together in order to come from a laboratory to a full-scale technical process. And then in the end, that the ODC platform we developed actually allows now much, much more beyond chlorine chemistry. Or to answer my question, can you increase the efficiency by 25% on a process that has been around for more than 100 years? Yes, you can. Thank you very much for your attention. Looking forward to your questions and comments. Thank you very much.
Thank you, sir, for this enlightening lecture. I now request to stop the recording.